Hello guys, this is Prime Concept. We want to push further on our studies under dimensional analysis. If you have not seen my previous video on dimensions, do well to check on my channel. Check the playlist under units, measurement and dimensions. You will see the videos in sequential order so that it can help you understand what we're going to do now. Now, very quickly, we have introduced unit measurement and we have also introduced dimensional analysis. So we want to get deeper into the analysis and dimensions. But let's start this way. Let's look at classification of physical quantities. Classification of physical quantities based on dimension. We can classify physical quantities into different categories based on their dimension, and this is very important because the exam would always ask you these things. So number one classification is you can classify them as dimensional variables. So physical quantities can be classified as one dimensional variables. Now, what are dimensional variables? Dimensional variables are variables or are physical quantities that have dimensions, and these physical quantities can have different values. For example, what we mean is, for example, velocity. We know that velocity is a variable. Velocity can take on different values. Velocity of a quantity can be 1, can be 10, can be 0. It can be anything minus 1. So velocity on its own is a variable. And because velocity has dimension, then we say velocity is a dimensional variable. And what is the dimension of velocity? We derive the dimension to be L t to the power minus 1. Acceleration is another example. Force is another example. These are dimensional variables because these things are not constant. They are variables. So this thing can change. Now, number 2 is what we know as dimensional constants. So when you say dimensional constants, these are fixed quantities. They are physical quantities whose values are what? Fixed, and they also have dimension. That's why I say it is dimensional. So they are physical quantities with they have fixed values, and they also have dimensions. That's why we call them dimensional quantities. An example would include acceleration due to gravity. Acceleration due to gravity is denoted by the symbol g. It's a constant, and we know acceleration due to gravity is usually 10, or you say 9.8, but it's a constant. So, and this particular constant has a dimension. And what is the dimension? It has a unit first of all. What is the dimension? The dimension is L t to the power minus 2. So this is an example of a dimensional constant. It's a constant, but it has dimension. So that's why we call it dimensional constants. Number 3, another example is capital G, which is universal gravitational constant. You know it, capital G. We derived the dimension in our previous video. Universal gravitational constant is also a constant. I think the value is 6.67 times 10 to the power minus 11, I think. So it's a constant also, but this constant has what? A dimension. So that's why we call it dimensional what? Constant. Another one is capital R, which is universal gas constant. universal gas constant, right? So this is also a constant. That's a value of 8.314, right? 8.314 joule per mole, joule per mole per Kelvin. So that is the unit. So you can also derive the dimension. So this is a constant. It means that the value is fixed. 8.314 is fixed, but it has a dimension. So these kind of quantities are called dimensional quantities. The exam would ask you all these things. So take them very serious. Now, number three, we have looked at dimensional variables, dimensional constants. We want to look at dimensionless const variable. Let's start with dimensionless variables. Dimensionless variables. Now, remember, you already know that variables are physical quantities whose values can change, right? That is variables. Now, we have variables that do not have dimension. So these kind of variables are called dimensionless variables, right? Example of these variables would include angle. Angle would include um would include strain would include would include strain, would include what else? Okay, let's say specific gravity. Specific gravity. Now, what is actually specific gravity? Specific gravity can also be called relative density. Now, all these are dimensionless variables. You will have more. I don't want to waste more time. Now, angle. Remember, angle can be measured in radian, or you can measure it in degree. It has a unit. Take note of this. Angle has a unit. The unit of angle is radian or degree, but angle does not have dimension. So they can still ask you which of the following is has a unit but is dimensionless. Angle has a unit but it is dimensionless. It does not have dimension. So if we check it, you would see that angle does not have dimension, right? So angle can be, you can talk about angle. So let me help you verify. Angle is actually same as arc radius over arc length, right? So that is angle, arc radius over arc length. So, and you know that radius is actually has a dimension of L, length has a dimension of L. So when this goes, you see that angle does not have dimension, right? But then angle is measured in radians. So it has units, but it does not have what? Dimension. So another thing is strain. Strain is actually extension over length. Now, what is the dimension of extension? It is capital L. Alright, I had to pause the video because of noise, right? But it has reduced. Now, what is strain? Strain is extension over length. And the dimension of extension is capital L. The dimension of length is capital L. So when this goes, you would see that strain is dimensionless. Take note, strain is both unitless and dimensionless, right? And the third one I mentioned there is specific gravity. Specific gravity, which I said is the same thing as relative density. So it means that it's the ratio of two densities. It's the ratio of density of a substance to density of water. So density of a substance to density of water. Now density has the same unit, the same dimension, so it means it would fizzle out. So you see that it's also dimensionless. So these are examples of dimensionless variables because angle can have any value 20, 10, 30, 50, 100. Strain can have any value. Specific gravity can have any value. They are variables, but because they don't have dimensions, we say they are dimensionless variables. Number 4 and the last is dimensionless constants. Dimensionless constants. Dimensionless constants. What are dimensionless constants? Of course, from the term constant, it means that these are fixed values. These are fixed values. They are physical quantities that have fixed values and they do not have dimensions. These are fixed values that don't have dimension. Example of dimensionless constants would include the Euler's number E, which I think is it 2.7 something now? That is Euler's number, is in your calculator. So it's a constant, just similar to the pi. Pi is also a constant, 3.142 and so on. It does not have dimensions, it's a constant. They are numbers. Then other numbers such as 1, 2, 3, 4, half, 1 over 3, and so on. All these are known as dimensionless constants. Dimensionless what? Constants. So I believe that this is very clear to you. Now, I want to quickly look at rules. Rules in dimensional analysis. Rules in dimensional analysis. These are very important. If you know the rules, then you can solve any problem. Trust me, you'll be able to solve any problem under the dimensional analysis. What are the rules in dimensional analysis? The rules, number 1, which is general. Number 1 actually encompasses all other rules, but I'm still going to split them. So number 1 is known as principle of homogeneity. Principle of homogeneity, that is number 1, which is a universal rule, which is something you should know. What is the principle of homogeneity? The principle of homogeneity says that if a physical equation, or if you have a physical equation, then for that equation to be correct, the dimension of the left-hand side should be equal or should be the same as the dimension of the right-hand side. That is the principle of homogeneity. Let me write it. For a physical equation, the dimension of left-hand side should equal that of right-hand side. That is the principle of homogeneity, which is very important, very simple. So let me give you a simple example. Say they say that, let's say they told you that S is equal to half AT squared. They say S is equal to half AT squared. Now, and they tell you that the dimension of S is capital L. For this equation to be true, it means that if the dimension of S is capital L, the dimension of this side should also be capital L. So let's check. Our left-hand side, which is S, that is the left-hand side, the dimension is capital L. So let's check the dimension of the right-hand side. So remember, 1 over 2 is a dimensionless constant. We're still going to mention the rules. So let's look at this dimensionless constant, which means it does not have, is a constant and it does not have dimension. So there's no point to worry about it. Then our acceleration, we know the dimension as Lt to the power minus 2. Then our time, we'll have the dimension as t. Then this is square, so t squared. So let's check. You would see that minus 2 plus 2 is 0. So this t would go. You'll be left with only L. So if you consider, you see that the dimension of the left-hand side is L. The dimension of the right-hand side is L. So this equation is correct. So it means that we have obeyed the principle of homogeneity. So the principle says that the dimension of the left hand side of a physical equation should be the same as the dimension of the what? Right hand side. That's the first principle. And you see that this principle in itself can be applied to solving complex problems. As simple as it looks, you would see the applications. Number two, we're looking at rules. Number two, we want to talk of addition and subtraction rule. That's what I call it, addition and subtraction rule. What does this rule say? That two or more physical quantities can be added or subtracted only if they have the same dimension. Two or more physical quantities can be added or subtracted only if they have same dimension. That is what this addition and subtraction rule says. So it means that if I say that A is equals B plus C, what it means is that the dimension of B should be the same as the dimension of C. That is only when this addition is possible. So if the dimension of B and C are the same, it would also mean that the dimension of B plus C would be the same as the dimension of A from the principle of homogeneity. So you can see how they connect. So same thing as subtraction. So this is very important. So when you are adding physical quantities, it means that their dimensions or equations should be, or units, should be the same. Then number three rule in dimensional analysis is that dimensionless constants are ignored. They are ignored in the analysis. Dimensionless constants are what? Ignored in the analysis. Just like you saw when I analyzed s equals half at squared, you notice that half is a dimensionless constant. It does not have dimension, so I ignored it. It does not participate in dimensional analysis. So I believe these rules are very clear to us. Now we want to look at applications of dimensional analysis, which is where the whole thing lies. Applications of dimensional analysis. Very important. Applications, right? Yes. Applications. And what are the applications of dimensional analysis? Number one very important application is that it is used to check the correctness of a physical equation. It is used to check the correctness of a physical equation. So you want to check if a physical equation is correct, then dimensional analysis can help us. Let's take an example under this, just one example, then we'll go to the next one, after which you can tie it up with different examples in our next video. Let's look at one example here. So I have this question. So the question says, which of the following equations is dimensionally correct? That's the question. So I have options, which I will just go straight and do one. So I have v squared equals u squared plus 2a. I have B, option B, v squared equals u squared plus 2as. Option C, I have v square equals u plus at. Option D, I have v equals u plus 2as. So these are the options I have for this question. So they said which of the following equation is dimensionally correct. Now remember, for an equation to be dimensionally correct, from principle of homogeneity, the left hand side dimension should be equal to the right hand side dimension. So for each of these things, we want to check their left hand side and right hand side. So that I don't waste time, I'm going to go straight because I know the correct one. If you already know equations of motion, you would know that this is the correct one. Every other one is wrong, so I don't waste time. From equation of motion, v square is equal to u square plus 2as. V square equals u square plus 2a is not correct because there's no s. So this is not correct. V square, this is supposed to be v equals u plus at. This is supposed to be v, because this is supposed to be v square equals u square plus 2as. So this is the correct one. So since it is the correct one, let me show you why it is the correct one, so that I don't waste time going through all of them. But under exam, say you don't know, you have to check all of them one after the other. But if you understand the equations, you can pick. So let's check. For option D, let's check the left hand side. So the left hand side is v square. And what is the dimension of v? Dimension of v is l t to power minus 1. Then this is all squared. So let's open it. So this is going to be l. This 2 would multiply the power 1 here, it becomes l2. Then t, this 2 would multiply minus 1, it becomes minus 2. So this is the dimension of the left hand side, l squared t to power minus 2. Let's verify the dimension of the right hand side, which is this. Our right hand side, which is u squared plus 2as. Remember, addition is possible if and only if their dimensions are what? The same. So let's look at, should I rub this? Okay, let me rub this side. So I want to find for u squared. And remember, u is still velocity. So for u squared is actually going to be L, because it is still velocity, is going to be L squared t to power minus 2. This is u squared. So this is what it will be. So for 2as, remember 2 is a dimensionless constant, so you don't consider it. So a, which is acceleration, is L t to power minus 2. S, which is distance, is L. So that this will give you L times L is L squared, then t to power minus 2. Now, for you to add up these two, your right hand side is going to be the addition of this and this, which is this and this. So L squared t to power minus 2 plus this, which is L squared t to power minus 2. If you add this up, you can say it is 2L squared t to power minus 2. But remember, in dimension, constants are not necessary. Dimensionless constants are not necessary. So our right hand side is, so if you ignore this constant because it is not necessary, our right hand side dimension is L squared t to power minus 2. Our left hand side dimension is L squared t to power minus 2. So because, therefore, left hand side equals right hand side, it means that that equation B is actually what? The correct equation. So that is one of the applications of dimensional analysis, to determine the correctness of a physical equation. Quickly, number 2 application is that it can be used to determine units of a physical quantity. It can be used to determine units of a physical quantity. So that is number 2 application. You can use it to determine units, right? So let's quickly show how that can be done. So for example, say we have velocity, and we know that the dimension of velocity is this. So how do we determine the unit of velocity knowing the dimension or given the dimension? It's simple. We know that L is the dimension for length, and length is measured in what? Meters. We know that capital T is the dimension for time, and time is measured in what? Seconds. So I have 2 power minus 1. So it means that the unit of velocity is meter per second. That is what it means. So that is the second application. The third application is that dimension or dimensional analysis can be used to suggest the relationship between physical quantities. It can be used to suggest the relation between physical quantities. When we say suggest, is a very important term and is a strong term. Now, notice I did not say dimensional analysis can be used to determine the relation, right? The reason is because dimensional analysis is limited. I'm still going to talk about the limitations. It's limited in the sense that it cannot account for dimensionless constants. So it means that dimensional analysis can only suggest. It can tell you this is the possible formula, or it may not be correct in some cases. In some other cases, it might be correct because in some cases it would then exclude the constants if they're actually constants there. So that is why we say it can be used to suggest the relationship between physical quantities. For example, they give you something like this. Somebody said the dimension of acceleration is actually L(t) to power minus 2. When somebody gives you this dimension, from this dimension you can suggest, you can suspect what the relationship for acceleration would be. So let's see how we can do that. First, you would see that from this, I can say this is L all over. I can bring this T down. It becomes T to power 2. Now, I know that L stands for distance or length. So I can quickly say that this is what? Distance, right? Yes. And then I would see that, okay, this is time, T squared. So I can quickly say that T, this is the dimension for time. So I can say time, this is time, or let's do it this way. We can say this is time times what? Time, because this is T squared. So that we can quickly now see that this part, distance over time, represents something very special. So you can see that distance over time is actually velocity. So I can now say this is velocity, then I have one of the time left under over what? Time. So it means I can say, okay, it's possible that the formula for acceleration is going to be what? Velocity over what? Time. Right? Yes. So the same way you can use that. See why we say it suggests. It cannot actually give us the correct unit always. See why we say it suggests. Now say we have something like this. Kinetic energy. Let's say kinetic energy, and somebody tells you that the dimension of kinetic energy, let me think of the dimension and write it so that we can now from there determine the formula or the equation. Dimension is m, so mlt to power minus 1. So this is the dimension. So somebody gives you, so that this is the dimension of kinetic energy. They now say determine the relation or the equation or the formula for kinetic energy. Let's see how we can do that. So this would be capital M represents mass. So it means I'll say, okay, in kinetic energy there is mass. So I can say mass times this is length or distance. So I can say, okay, this is distance, then over what? This is time, right? Time, this is time. Sorry, I made a mistake. the dimension of this, sorry, is L square T to the power minus 2. So this is a mistake. So now we'll say this is mass, which is m. Then this, I can decide to write this as, okay, L squared over what? T. If I bring this down, it becomes T squared, right? Yes, so I can say this is mass, which is m, times this is L over T. I can decide to put the square like this, so that this becomes mass times, now L is distance and capital T is time. So this is distance over time, which is velocity. So I can put this whole thing in bracket as velocity, then all what? Squared. All squared. Now you now see that I've been able to deduce that the formula for kinetic energy is what? mv squared. But what did you notice? You notice that this dimensional analysis that I used in deducing this formula omitted something, because we know that the correct formula for kinetic energy, the correct formula is half mv squared. So you see that though this one tried, but it omitted what? Half. And that is why we say that dimensional analysis can be used to suggest. So you can say that it is suggesting to you that in the formula of kinetic energy, there is mv squared. But if there is a dimensionless constant, I don't know. But definitely there is what? mv squared. That is what dimensional analysis will do for you. It would suggest the relationship. In some cases, it might be correct, like in this case. In some other cases where there is a dimensionless constant, it will fail. So that is it. These are the three major applications of dimensional analysis. So remember, I was still going to solve problems, more serious problems, based on these applications. But to tidy up this part of the video, I'm going to now mention the limitations of dimensional analysis. Limitations. Number one limitation, which you have obviously seen, is that it cannot, or you say it does not account for dimensionless constants. It does not account for dimensionless constants, just like we see. It failed in introducing half in our derivation. So that is one of the major limitations in dimensional analysis. Another limitation is that it does not determine whether a physical quantity is vector or scalar. So it cannot tell you whether a physical quantity is a vector quantity or whether physical quantity is a what? Scalar quantity. So this is one of the limitations of dimensional analysis. So you just know, but cannot really tell whether it is vector or what? Scalar. So these are major limitations in using dimensional analysis. We have more, so you can add more to the list. If you know more limitations to this, drop the answers in the comment section. Tell me this is also another limitation you have noticed with dimensional analysis. So I believe that at this point, the concept of dimensional analysis is really very clear to you. In my next video, I'll look at strong questions that applies the rules I've explained here and the application. So do well to follow this channel so that the next application you would learn how to solve it. Thanks for watching this video, Prime Concept.